Hey, folks. We are live to the world from Albuquerque, New Mexico. It's noon on T2sday. This is an experiment. There's folks watching on the live stream. Hi, everybody. It really makes it exciting. I want to explain what we just looked at, and that's going to be the major activity of this update, as well as just trying to kick the tires on this crazy stuff. So let's get into it. Where's my finding my way around? There we go. Okay. So for those of us who are just joining us, what is this all about? What is the T2 project all about? It's about building indefinitely scalable systems. I find that when we build engineering systems, we just build a machine, and a machine has edges. And what we tend to do is throw all the inconvenient stuff to the edge, all the waste, the garbage, the pollution, the cost to society, and so forth. We push them to the edge and let them drop. The idea of indefinite scalability is saying, no, what if you can't do that? What if you have to build the system and your design has to go arbitrarily far? So it has to account for everything. In computing, that means we have to give up on the idea of central processing and random access memory. We have to give up on the idea of deterministic execution, that computers are completely repeatable. How are we going to do it? Well, that's what the T2 project is all about. We start with an individual little piece of hardware, a tile like this one. This is the T2 tile that we've been working on for the last many years now. The point is we can repeat this and make as many as we want and connect it to copies of itself. The point is it's all completely decentralized and bottom up. Often in parallel computing systems, there's like a head node, a big cheese, someone who's in charge. We don't have that here. It's all working from the bottom, and each individual tile, as far as it knows, it's the center of the universe. It's kind of like people. To go with that, I mean, that's a very different way to compute than thinking everything. I'm in charge of everything. I'm the central processor. Everybody just waits until I tell them what to do. As a result, we need a whole new best effort software stack, because these things might crap out individually without the whole grid going down. So that's what we're trying to do. We've built hardware. We've got simulators of the hardware. Most of what we've been doing for the last several months has been in the simulation. The hardware still needs some work, and we're going to be getting back to that soon. But why make this whole effort? We've got computers. The reason I am motivated to do this is I am seriously concerned about the future of information technological society. Now, maybe we're all going to die of pandemics or the next fungal plague or whatever it is anyway, but assuming we manage to get past that, assuming we manage to hold some kind of actual organization that allows for innovation and that allows for liberty and bottom-up influences to persist. I'm concerned about the computer technology base that we have. Based on CPU and RAM, it's incredibly fragile, it's incredibly brittle, and it's essentially impossible to make secure. And we don't even want just security. What we want is loyalty. And it doesn't even make sense to say, how could a machine be loyal? And the reason it doesn't make sense is because our machines don't know us. And computers say, Facebook has so much data about us. Yeah, but they're not our friends. They don't have our best interests at heart. We want our hardware to be ours and will live and die with us. That's the goal. That's a pretty big goal. That's pretty ambitious. A whole new type of hardware, a whole new approach, a whole new software stack. When is it going to be here? When is it going to run Excel spreadsheets? And the answer is, this is a research and development project. When is it coming? Closer than it was 2 weeks ago. And where this whole story just ended, last update, was we had taken this idea of a tectonic plate, a little solid block of atoms that we could customize to do what we want, and said, well, what if we pop them out and spread them out so they had some empty space in between them, and we could put other things in there. Last time we made a crossbar switch. This time we made something else. My repeating goal in this is, this is a crazy, spatially distributed cellular automata, new kind of computing architecture. Well, not that new. People have been studying cellular automata in various shapes and forms all the way back since the beginning. In the details, with the engineering focus, yes, very different. The main difference is Oh, I'm cropped off here. Paths to utility. That the goal is not to imitate life directly. That may be helpful to get something done, but that's not the top order purpose of it. The purpose is to figure out a way to do engineering on this sort of thing in a way that could actually be useful to society. That we could build, future tile grids that would control systems. That you might not be insane to let them near you because they would be beholden to you. They would be your buddies. I suppose they might get pissed at you from time to time, but they're yours. They will die for you. That's what we're looking for. And the paths to utility, this episode goes through closed box function optimization. That used to be called black box function optimization, but now we're trying to find terms that are less less color oriented. So closed box versus open box. In an open box function optimization, you're allowed to look at the details of the function. You say, oh, this is a linear function, this is a quadratic function, oh, I know what to do with this. In the closed box function optimization, all you've got is, where is it? You send points off to the function and you get back values to the search strategy. And the search strategy's job is to figure out what points to send to the function in order to get higher and higher values back. Separate from the search strategy, there's some kind of observer that decides when we're done good enough or we haven't done good enough and we just have to give up. And that's what we're doing here. So, oh dear, right. Stochastic iterated genetic hill climbing, SIGH, S-I-G-H. It's an algorithm for doing closed box function optimization. And it's the algorithm that I wrote my PhD dissertation on in the 1980s. These days people do such a great job, doing, Twitter threads and Instagram pictures and all kinds of live public posts about to explain their thesis research, and I'm just a little bit behind. The way SIGH works, it's a neural net. So it has a bunch of units, a bunch of decision units that can be on or off that represent the value, the point that we're going to evaluate in the function. In this model, that's called the government. The idea, it's based on an election. We have a population of voters, and the voters somehow vote on 0 or 1 for each position in the government. And then when we have a complete government, that gets off to be evaluated by the black box function. And the goal is for the voters to figure out ways to elect governments that lead to success. This, in a lot of ways, it's very natural. It's very common. So we have these. Where is it? We have. Oh yeah, I keep forgetting. I'm live, so I'm supposed to be able to do this. It's a little bit backwards though, so I'm still learning. Right. So here's the government positions, and then down here is the population. The governments are all plus or minus 1 or 0, but the voters have 3 choices. They can support a particular set of candidates with a plus, they can oppose a particular set of candidates with a minus, or they can adopt state 0, meaning they're apathetic and I could give a crap. And in the learning algorithm works, if you support or oppose, either way, the result of the black box function coming back will descend upon you. If you picked something that produced a value that's judged good and you supported it, your weights get bigger. If you picked something that turns out to produce a score that ends up with a negative reinforcement, then your weights go down. If you're apathetic, your weights don't change. And that's how it works. Is it a great, amazing, does it beat a world at all other approaches to closed box function optimization? No, it doesn't. But it depends on how you count. The easiest thing to count is how many evaluations of the function does it take in order to actually find the best possible value, or find a value that, the observer is willing to judge as successful, like that. But that's just one approach. And so what we've got now, what is new this week, is and here's the actual rule. This is from the book, from my dissertation, like that. It's got these various phases. So first you hold an election, which is you let all of the voters stay constant and they vote for what the government wants to be, and then at the end of that you decide who won the election, and now you have the reaction where the voters get to decide if they like the government or not, and then we have the consequences. consequences, where we take the result of the government, we get it evaluated by the the closed box function, and we decide how well we're doing. That's what that's what this is. I mean, it's pretty complicated. It's got all kinds of stuff going on, and it's got, what the heck is this? It's got a FUT. There it is. It's got the FUT. That's the function under test. Let's break this down just a little bit, just to get the idea so that we understand maybe what we saw at the beginning. So all of this started as the typical with these computations with a single seed. This is an SW, a seed weight matrix. And, what happens is you put down a single one of these. The first time it gets an event, assuming there's empty space around, it pops out into some initial configuration. In cellular automata, they usually call them a Garden of Eden configuration, because it didn't come from any previous state of the cellular automata. In the case of the movable feast machine, what we're doing, the concept of a Garden of Eden state isn't as obvious, because since there's a certain amount of randomness and computations don't happen the same way, the fact of a particular configuration being impossible to produce by the rules, it really is less likely to come up. So, in any case, on the first event, this thing pops out to its initial configuration. And look at that. That's really complicated. 1, 2, 3. That's nine atoms in the initial configuration. And each one of those is doing one of the things, something that's important for a thing. Well, let me use the mouse. Still do that, right? Yeah, here we are. So SO, that's the psi operator. That's the thing that's going to run the whole operation. The VV is the vector of voters that we saw along the bottom of the image. The PQ is it's a vector that's a vertical vector. The poll questions, the elected offices, whatever it happens to be. And these two WMs are going to be weight matrices. And the way these weight matrices work is they're inherently asymmetric. They're going from this to that, or from this to that. And I've got versions which handle the various rotations. So this upper WM is the one that's coming out of the poll questions, that's broadcasting the results of the election so that all the voters can see it. This one down here is broadcasting the result of a single voter's choices, so all the government offices, the poll questions, can see it. And the SGs are state gates. Now, one of the things I was really interested to try to do, but I just couldn't take the time. Well, I couldn't get it working. The psi algorithm is broken down into these phases. First, you hold a vote, wait for it to be done. Then you have the reaction, wait for it to be done. Then you have consequences, wait for it to be done, and then vote again. But in this model, it might be really kind of interesting to not bother to break those phases down quite so much. I haven't tried it yet. It's just one of those things, hope that one day there'll be enough time to it. So given that we don't want to do that, we actually want to say, no, the voters should ignore everything that's happening until it's their turn to vote. Then and only then should we grab what they're thinking at that moment and have that be the vote. That's their moment in the polling booth. And that's what this SG is for. That's what this state gate is for. The psi operator is going to trigger the state gate on the voter vector when it's time for them to do their thing. And we're going to, as quickly as we can, it has to propagate down the steps, capture everybody's vote, and then latch it, and then keep it. And the state gate up here is the same thing, except that's for deciding the result of the election, like that. So the psi operator triggers the state gates in turn to create the vote react cycle. The EV over here is the evaluation thing. That's actually another state gate, although it's not colored quite the same way, that the psi operator uses when it's time to say, okay, what was the results? I have to actually pass this result off to the black box. I keep saying it. The closed box function to get a score. Now, in a better implementation of this, the function to be optimized would really be more weight matrices, more things that would be evaluating what this system did to decide whether they like it or not. But for purposes of this demo, I cheat, and the EVs, which we'll see stacking up in a second, they just fold all the bits down into a single little word and then pass it off to one individual atom, which evaluates it. And then here's the key. How do you know if a function value of 115 is good, or 1012 is good or bad? Or, how do you tell? The psi algorithm is based on reinforcement comparison. The idea is we remember a running backwards average of all the function values we've seen. And if the one that we get now is better than the running backwards average, then we say, hey, you did something good. That's a positive reinforcement. If it's worse than the running backwards average, then we say that's punishment. Now, of course, no matter what it is, it's going to pull the backwards average in the direction that it goes a little bit. So with that approach, we could just freeze up. We could get a score of 1,000. Oh, that seems great. And now the reinforcement is 0, but that's okay. Everybody just says, let's keep doing the thing that gets 1,000. I'm good with it. There might never be any more searching. So the additional parameter in the psi algorithm is called, I don't even remember what it is. Well, it's called delta, but it basically, it's the ambition. It's the restlessness. So that instead of just comparing the backwards average to the current score and saying, if it's exact match, the reinforcement is 0, we add in a little expectation. The value of the function needs to keep increasing a little bit, or else the reinforcement eventually goes negative. So we can see it, and it does happen in the opening video that was going all over the place, that the government freezes up, and the same parties get elected over and over and over again. And in this particular case, the evaluation, the black box, the closed box function, produces the same result over and over again. Now, that wouldn't necessarily be true in general, but it's true here. And so eventually the reinforcement goes negative, and eventually the negative reinforcement starts to melt away the weight matrices until the voters start getting apathetic and they start flipping over to oppose things they supported, or vice versa, and the whole system melts. So you get this interesting long-term behavior, which, I could see behaviors like that in my own thinking of myself as a closed box function optimizer, trying to make something do something, like, for example, trying to get code to work. And, I could make different decisions about how much ambition I would have. And, so once I got something to work, I would be excited about it for a while, but then, it's boring. I wanted to do something cooler, so I tear it up. Psi just does that because of the reinforcement and the delta, the reinforcement comparison, that what we're really looking for is improvement by this much. And that if we get negative reinforcement, what that tends to do, the way it works through the algebra, is it tends to make the weights in the matrices smaller, closer to 0, whether they're positive or negative, which makes the system more random. And that's it. So the seed pops out into the initial configuration, the egg, which then grows. And did I mention RM? I don't know if I did. RM is the reinforcement matrix. Because, once we've gotten the reinforcement score, we said, oh, that was an improvement. We need to tell all the weights in both the networks, from the voters to the government, from the government back to the voters, what happened, so that the weights can be updated. That's what the reinforcement matrix does. It carries the reinforcement out to the grid. And that's the main thing that you see in the opening video, this kind of red wave sweeping out and then blue pulling back in. That's the reinforcement matrix distributing the results to the weight matrix and then coming back. All right, and here's the whole thing. So we can see, right? We've got the psi operator. He's a little state machine going in a loop. Here's the function under test. The last value that it evaluated was 17,920. The backwards average value was 15,220. So we did better. So the last reinforcement was positive. In this case, it's 2, and so on. And, how well is it working? I'm not completely sure. Why don't we try it? We won't get to see it. Let's just try it for a minute or two before we run out of time. Let's see if I can get this to go. All right, I think that's it. So we'll get ourselves a seed, and we'll fire it off. And there we go. And let's get some atom viewers here. Here's our FUT and our psi operator, so we can tell. Whoops, Oh, that's what it was. I hit the wrong numbers. All right. So, at the moment, and the video does switch in the middle. Right now, yeah, it's hard to see because it's better when it's going fast because then you see the snappier decisions. In the early part of the video, we'll watch it once again to close out this thing, and hopefully we'll see it with slightly clearer eyes. That when the voters are making their decisions, the vertical lines tend to change colors. So there was a horizontal one going. So that's the results of an election being distributed back and so forth. And now the psi operators in state 4, which means it's actually going off to evaluate the thing like that. Does it work? Well, what's the FUT? What's the function under test? In this particular case, what it's trying to do, again, the psi construction, the nodes, the voters, the poll questions, the weight matrices have no idea of this. It's hidden down inside the FUT. The way you improve the score is by having as many of the poll questions green, as many set as possible, except the number of them set needs to be a multiple of 3. So now, and one other thing, one other thing that in one of the basic things that happens in weight matrices, if you just have every unit, every vector of this thing connected to every vector of this thing, and they're going back and forth, then they have no real orientation. If this guy if one of these beings wants to be on by default, it's got no way to do it because all of its inputs are coming from the flexible, the variable state on the other side. So in this particular case, the very top question in the poll question is a true unit. It means the result is always green no matter what the vote is. And the same thing, maybe we should switch. It's really hard to tell. This is what it looks like, just the element view without showing anything that depends on the actual specifics of the network. But it's more fun to do it. So this column out here is the true unit, and this row over here is the true unit. So when we're evaluating the score, we chop that one off. So we take all of these other ones: green, green, red, green, 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 green. So that's 1, 2, 3, 4, 5, 6, 7 greens, and 1, 2, 3 red, like that. So 7, 3 mod 4. 7 is 3 mod 4. So in fact, it looks like it's optimized the function here. If it turned any of these 3 on, it would have more on, which gets it some bonus, but then it would no longer be equal to 3 mod 4, the count, so it would pay a penalty, and so on. Did the job. Yay, sigh. Not that this is that hard a function, not that it's that big a function, etc., etc., etc. But hey, function optimization doesn't go away. It comes up all over the place, and to have something that's reasonably general, that it makes very few assumptions. It doesn't know that positive that it should be expecting to reach 100 or 1,000 or whatever. As far as it could be that minus 10,000 is the best possible score, and the reinforcement comparison mechanism would automatically home in on that. Okay. So that's it. Now, the one thing that I did want to mention, and then I will wrap up, is, with the psi operator sequencing it so that the entire voter vector goes and then the entire poll question vector goes, it doesn't matter where you actually are on any given vector here. But what I wanted to do was to let them go in their own time, so that because when we distribute a reinforcement signal, it emerges from the lower left corner and arrives at those parts of the weight matrices sooner. And we do all of this extra work with all the sequencing so that, in effect, everybody gets a fair chance. But what if we didn't do that? What if we put the things that we wanted to be fast, like reflexes, spinal cord, stuff like that, if we arranged for that stuff to be represented near the head, near the action, and we could have fast learning loops going between, the few key voters and the few key election positions, and then slower and more general and more vague stuff. And if the reinforcement gets a little bit muddy out there because, it's some combination of the previous election and the current election, well, maybe that'll be helpful. Maybe that'll allow those guys to pick up the more general, bigger landscape features rather than getting hung up about every last little point on every little fast time scale. That would be for the future. Okay, so we'll let this stop this guy. All right. So that's it. So all of this, the reason that we're happening live, and we've got concurrent viewers. Look at all these folks. Thank you so much for coming. I haven't been able to look at the chat while I've been doing this, but I will stick around. I guess after it works. I'm not sure. I'm not sure what happens when I end the stream. I really haven't ended a stream before. All of this is possible because I finally broke down and installed Ubuntu 20.04 on the workstation that we're seeing all this with, and played around with OBS, Open Broadcast Studio, which is super cool. It turned out that it didn't do Mac Screen, which I mentioned a few updates ago, out of the box, and it turned out to be harder than I expected to do Mac Screen. But I came up with an amazingly disgusting hack, which is what we are using. And it actually works not too terribly. As the screen is kind of fuzzy, and that's my biggest concern about it. That's not entirely because of my hack, although it may be partly because of the hack. So, yes, everybody bugging me to update. You were right. Thank you. Everybody telling me, like Andrew, to try OBS. Yes, you were right. And if this all works out, if I get better at this, I would like to be using this more often for more stuff. For example, I am participating in a Zoom workshop the rest of this week, starting tomorrow, and I may use this as well. The SFI, Santa Fe Institute Workshop on the Frontiers of Evolutionary Computing. Next week I've got one as well. It just keeps coming. The next update will be on August 3rd, and thank you all, folks, for coming. Tell you what, I'm just going to rerun the opener and catch up and try to read these comments for the last minute or two. But anyway, where are we here? Thanks, folks. This was fun. So you see the red stuff going forward and back, that's the reinforcement matrix. Right now, the colors, the blues, the greens, that means the weights are big. It's using a rainbow display. And that's because the FUT is basically locked. Oh, and it just melted. And so you see the colors have gone back to more green, which is the range of 0 weights, and now they're actually, it looks like they're starting to grow again. And that's exactly the kind of thing that you get with Psi. You get this excitement of convergence. This is the guy for us. Bam, bam, bam. Look at that. Look at all those reds and blues. Those are big positive and negative weights. And I think it's going to end. Yeah, it's going to end. All right. I'm gonna end the stream here because I'm jittering. Hope to see everybody next time.